Welcome to the Embedded App of the Day. So in the remaining classes, I'm going to try and show a different application of embedded systems. Guys, I can't do this, and I can't record if you're all talking. So today's app of the day is this. What is that? Oh, somebody said it right. It's a Hallmark color. Here we go. Let's see if you can hear this. All right. Wasn't that exciting? Yeah. But I'd like you to take a look at this app. It's something simple. By the way, when you open the card, this little thing here slides, and it's actually in this hole where it slides, and it makes the contact. So let's say you have the card closed, and I took everything away, and then you open the card, and then it closes back up. But this is a neat little app because think about this. This is sold as a greeting card for somewhere between $4 and $5, and it some of these actually will allow you to record. This one just plays a song, so I'm sure they have to pay the estate of Johnny Cash a certain amount of money for using his song in this. But even the functionality, you take a look, you have probably one of the biggest costs is this part and that part. So what is that part right there? There we go. What does it look like? Speaker. And this looks like a battery. And then there's something over here with a big old glob of black goo. Have I talked about big globs of black goo and what's hidden underneath them? I think I showed that with a Furby, didn't I? So that big glob of goo is a chip below there. And you know how you've seen microprocessors, microcontrollers, they have big black pieces of plastic, and inside is the silicon. Well, that actually costs a lot of money to do that. So one simple way is to take a piece of silicon and just put it directly on a printed circuit board, do a little bit of wire bonding to some of the connections on the outside, and then just put this big old black piece of, or black goo of epoxy over it. And you can reduce the amount of money that it costs to make this part. And so that's one of the things they do to improve the price. It also is a bit changeable. Now imagine you have this wonderful device here, and you want to maybe put another recording on it. Or maybe you want to manufacture the chip down here to actually have several different recordings, and the one you play is maybe set by that resistor value. So what happens if I change that resistor value? Will it come up with a new song? Let's see. This is just I'm shorting this. Yeah, didn't do it. Let's see if there's something else. Oh, this did it better last time. There you go. Let's do it again. All right, so apparently when I do that, it speeds it up and makes it sound like Donald Duck or something like that. So And for those of you who didn't guess what it was, yes, it is a Hallmark card. Ring of Fire, written by June Carter. June Carter, if you know, that's Jimmy Carter's. This is Johnny Cash's wife. So this is today's embedded app of the day. One thing I should make another point of, look at how inexpensive this whole board is. There's nothing on one side, and on this side it's only a little bit. So one of the aspects of many consumer products is make it as cheap as possible. And that is today's embedded app of the day, the Hallmark greeting card. Musical greeting card. Thank you very much. All right, today, lecture number 10 is the day that we're going to go over a little bit more of software engineering. And in particular, we're going to look at chapter number 4. So quickly, how many people actually read chapter 4? Oh man, how many of you have actually read the book at all, for anything? Yeah, only because there's some problems inside the book, right? All right, so wasn't homework 3 due today? Maybe. So again, what I'm going to cover is in chapter 4 of the book. And for those of you who have not even opened or cracked the book yet, this is a wonderful topic that we've spent lots and lots of time on doing, and that is software development tools. So I guess that I should step back a little bit and say, when you are actually going through and developing software, remember we talked about software engineering in our last class, right? And one thing I said is that how often are you going to be writing code? And the answer is not too often. However, usually in what you have to do, you will have to write some code as the initial design, and then later when you get a good idea of how things will work in the future and you need to beef it up more, maybe you'll be hiring somebody to take care of that. Maybe a co-op, maybe somebody with a bachelor's degree. Not all you people who are going to get masters and PhDs, right? So, remember earlier we said in software development, specifically, you're looking at the requirements. In other words, things like, oh, what are we going to have and how are we going to make this work? Then you go a little bit further into the design. You do things like algorithms. And then you'll go and you'll write the code. And then you will have to test. Initially, you'll do the unit test. Then you will start to integrate. And then, of course, you'll add software plus hardware. So, what I'm going to look at, and you've already had a little flavor of this, is how are you going to develop that code, and actually, what can you do to help with this major part of it, but also with this right here, help you integrate later on. And that's what's called an integrated development environment. Or our IDE. So imagine this. Imagine that you want to develop code as quickly as possible. The one way to do that is, first of all, you design. Remember, like I said up there, design. You write a general idea of what you want it to do. Now, we talked briefly about pseudocode, right? What do you think pseudocode would be useful for, by the way? And that's all I heard. And one person at a time. Ah, very good. Have I said that before? Or you just knew that? All right, great. You know what? Have you had a trip to the prize closet? All right, you got a trip to the prize closet. And you're the first one, all right? The first one today. The whole idea is that if you do the design up front and say, oh, at this point I want to read these certain values, they can serve immediately as your comments in the code, right? When should you be writing comments in the code? Not the last thing. In fact, never the last thing. Although I have had people tell me, oh yes, my code, my software is self-documenting. To yourself it is, all right? If anybody else were to pick that up, usually they have difficulty. That's why the best coders are those that actually write comments before they write the code. So, in our integrated development environment, it allows you to do several things. One is it allows you to write the code. It allows you to actually debug when you're writing your code. And the other nice feature of it is it handles the, very often handles the communications with the target. And it handles the download of object code. And I'm going to go into this in a lot of detail later on in this class, but the nice thing that you have to think about when you're using an integrated development environment is as follows. You have a PC. This is one of them old style PCs that's huge, right? And you connect it to your target. You run something on here which is called a cross compiler. In other words, what you're doing is you are generating executable software on a machine where that's not where it's going to run. Obviously, you're developing code for this target right here, which is your Renesas RX 62N board. And you're compiling it on a PC, which has a completely different microcontroller. And you have to obviously download what you generate over here to the target. This is something that has been done for years and years and years and years and years. For example, in the old days of Motorola, they generated something called S-Records, which allowed you to compile code, have it work on another device. And you could even port it either via RS-232 through any other communications device, or for that matter, you could burn it directly onto a chip and then take the chip away and put it in the device. But we won't go into that. So, if we fully look at all of the tools in an IDE, we have what?
Editor.
Say that louder?
Editor.
And an editor.
The project window.
By the way, does this editor, does it actually tell you some parsing type of things, like where you start and end a curly bracket, or maybe what's a comment, what's executable? So this is a full-featured editor. It'll allow you to search. It'll even allow you to search for keywords, variables, in all sorts of different files. All right. I think somebody else has said a project creator.
So Windows, a project window.
You got to say that louder.
Workspace window.
All right. It gives you a workspace. As I said earlier, one of the other things it does is it gives you a downloader, right? And then there are three major things that it also gives you, which is what you're interested in.
Compiler.
Compiler.
big or
Linker. Oh, that's right, it does have a simulator too, doesn't it? And that's the nice thing about this, is that if you use the simulator features of it, then you do not need to actually have a target there running. You can test some of the code just to test to make sure that it works. And in fact, that's one thing you could do to ensure that your code is working before you put it on the hardware. So, let's take a look at just a general concept of what do you need to know about your entire embedded system, right? Well, we're going to be developing code for this, so we should know some things about your target. So, what do you need to know? Your embedded system that you're going to be developing for. In other words, what do you need to know about the hardware?
Processor speed.
Ooh, I like that. Okay, hold on.
Memory.
Do we need to know specifically about, well, yeah, I'll put it down, memory. Well, what about the memory?
size.
Ooh, we need to know size. We need to know about RAM. We need to know about ROM. We need to know about the EEPROM equivalent. We need to know the size and location. Right? Because as your homework assignment showed you, right, you have this huge space from 0000, how many bits for an address?
5.
How many bits for an address total in our RX62N? 32 bits, right? So if we have hex 0000 as the very top one, the very last address is going to be FFFF. So you need to know where everything is going to be. And as you saw from the homework assignment, sometimes there's something that's going to be at the front. Sometimes something's going to be at the back. Usually we like to keep the flash or the code right here at the end. And we like to keep the RAM here at the front. And sometimes we even have to add in here the registers, or what we call the special function registers. Or those areas of memory map that we are going to be writing to. And then maybe we could also put our EEPROM in here. And that pretty much looks like what the homework assignment was, right? The only thing missing here is what the addresses are. But that's going to differ, because what we also have to know about is specifically which chip, right? The variant of the RX62. In other words, how much RAM? How much ROM? How much EEPROM? You also need to know if it's going to have any external. A chip will come with a certain amount of memory. It might not be enough. You may have to add in some SROM or SRAM or something else like that. or DRAM because you just don't have enough. And so you may have to set up your processor and add some extra space in here for extra RAM. And that's some of the things that you need to know about your embedded system. Now, in general, you also have to know
I.O. ports.
which I/O ports, all right? And that would be the definition or the mapping of I/O peripherals. And if, depending on what you're doing, what your target is, it may be external to the microcontroller. What's one example of a peripheral I/O device on your RX62N board? All right, you have oh yeah, I heard several things, so let me hear it again. Just one person. Raise your hand so I can. It's really easy. There's two that are really simple. They're digital ones. What would that be? Two peripheral devices, peripheral or outside of the chip itself. All right, switches, push buttons, and what else? What would be a nice output device from the processor? LEDs, right? So you need to identify where those are going to be held or where they're going to be used. Where do we define that stuff? Where do we define where these external to the microcontroller devices are? What kind of a file? It's an include file, right? A .h file? And actually, if you've looked in your project that you did for the last lab, it had all sorts of wonderful information in there as to what specific port is being used for this device and that device. So let's see, what else do we care about or we worry about? Ooh. Just in general, what do we need to worry about when we're doing our compiling? This is libraries. Tools, maybe some existing code. So, as an example, how many of you are done with Lab 2 already? Just with one, huh? So now I get to pick on you since you're finished, right? Did you demo it? Ah, so you're not done. Did I give you some code for this lab?
Yes.
Yeah. So that would be existing code. And very often when you're doing lots of projects, you start with existing code. So as an example, I worked for a company, we made mobile phones. Did we start from scratch every time we made a new phone? No. We took code from the previous version and tweaked it. Sometimes it was a lot of tweaks. But nonetheless, when you're communicating via GSM, let's say, and the next phone is also going to communicate using GSM, the standard usually doesn't change at all. So you can just use that code as is with no changes. What changes around it? That would be maybe how the display looks, maybe some of the menus, maybe the fact that you have a bigger screen. Now you can put more stuff on it. So you need to figure out how you're going to make that usable. So usually you start a project with existing code. So have you done that already for one of your labs? Remember we told you to use this, use the project creator for your integrated development environment, and then go ahead and just make some modifications. So very often that will be one way that you start, rather than starting from scratch, is you make some modifications. So let's take a look at really what's happening when we compile code. So remember I showed this picture here of a PC, and then I showed a picture over here of your target. And in this case it is your Renesas RX62N, which has all these wonderful I/O devices that you could work with, right? When you write code, are you writing directly to that microcontroller? The answer is no. Does anybody have a board here? There's one right here, right? Can I steal your board? I promise I won't spit on it or anything. It's like anybody remember that? Was it a Volkswagen commercial where somebody wants to make sure they keep the car and nobody buys it from them, so he goes up to the car handle and licks the handle? You'll never want this back, will you? No, you'll want it back. I know that. All right, let's take a look. Here's a microcontroller right here, right in the middle. And how do you communicate with it? With this up there, right? Just for grins, turn off this light, it gets better. So this is your target microcontroller. This is your communication. What do you see in between?
Tracks.
All right. So it looks like there's another chip up there. What in the heck is that there? So let's take a little look. Go down in great detail. See if we can see it. Did you scrape off the surface of that? All right, I can't see it. But anyhow, what it is actually another chip. It is another processor. And it turns out to be a... That would help, wouldn't it? An H8 debugger, but it also, what it does is it's a special device.
Trying to fix that autofocus? Weird.
And it has code written by Renesas. And in the process of developing your code, what it does is it communicates the code that you compile down to this device, which temporarily stores it, and then turns around and writes it out to this device. And it gets even better. When you actually run the debugger, what's controlling the entire board is that. Because you'll send the instruction, I want to start debugging, to this chip, and it will say, okay, Renesas RX62N, run one instruction. Then when you're done, I'm going to take and get all of your information that I want to use for debugging, and then I'll send it back to the PC so that they could display it. So what you have inside of this debugger chip is some ROM and some RAM. The ROM is flash and some RAM. The flash holds code which you are not changing at all, usually. And whenever you do the compile, sure, the code is eventually going to go over here, but there's something in the way. Now, there is a way that you can actually flash this chip, and it's some of the tools that you will need to update that every so often. But I'm not going to worry about that for now. So, what I would like to do is to go through a little bit of detail, but I'm looking out here and I'm seeing a lot of yawning. So let's take a quick break, 5 minutes to stretch, and then we'll start back up again. So. We are back for our embedded systems, the end of the day talk. And what I want to do is I'm going to go into a little bit of detail on what's happening with our specific device. In other words, how do we know that, or what is actually going on inside the compiler? Does anybody know? Or does everybody know? In our tools, how does it generate code to run? Who knows how that works?
Magic.
Wow, nobody, huh? Pay very close attention. This will be on a test. How the compiler, linker works on a test. So, if you look in the book, and this is a nice example of this, we have in the book a specific process that is followed for our compiler and our linker. So what you need to look at is the following. You have C, source, and header files. Header files will be .h files. Notice that this is not project files, because the project is used for organizing, for identifying everything that's going to be needed. But when you start generating code, the project file is not downloaded to your processor. The only thing downloaded all the way at the end to your processor is this executable image. So simply you start with the following. You have your source and header files, and then you have a piece of code in your IDE, which will be a preprocessor. It will make sure that you haven't done anything dumb in your compiling. So, for example, if you have a syntax error, this is when things will be identified. If you have some other, let's see, I'm trying to think. Oh, I know, the macros that you have, right? So what's a macro? What's one example of a macro? How to define, right? That's one example of a macro that you have. And so anytime it sees whatever you put after this, let's say you have something called port 0, it'll actually substitute in its place the real definition of what port 0 is. And maybe in the example of our board, port 0 is going to be the address 8C000, as an example. So anytime it sees port 0, it's going to insert that specific number, which is an address of where port C might exist. Also, as I said, the preprocessor will take care of syntax. Syntax, right? Everybody knows what syntax is? That's right, it's a tax on alcohol. That's a pun. All right, never mind. Go on. All right. Don't give up my day job. So once the C preprocessor has run, then the compiler will take a look at the C code, and at the same time will identify or create a symbol table. Now, I hope that you've had this in a previous class, what a symbol table is, right? A symbol table will be really a place where it's storing all the information like variables. So an example of a symbol in the symbol table might be integer I. And maybe this is a global because it exists somewhere out there. So it's going to say, oh yeah, integer I, this is going to be a global. And it keeps a table of this. And it actually puts it somewhere in memory that you can get to later. The other thing it might know is that, oh, the main program is going to be a label. It identifies a function that will be loaded somewhere in memory. Because somewhere, main is going to have to be called. Maybe you have a function called func. You've seen that before, right? That's also a function name that needs to be identified where it's going to be put, and that's going to be stored in the symbol table. The source code is analyzed and the target code is synthesized using what's identified in the symbol table, because remember, we're taking words that we've seen before and that we write, but it needs to be translated into specific addresses and locations for the code to run. The result of all of this is going to be an output that looks somewhat like assembly code. And it's actually machine code. So it is and those of you who have computer architecture, you have gone over that, right? When you compile, what does it get translated into for execution, right? I'm going to be looking at Josh. You did that, right? Okay, so you guys know what that is. That will be on the test. If you don't know, ask now. Okay, we go on. The machine language code cannot be executed on the target processor. Why not? Well, you don't know, or you don't have everything included in it. You need to add a few more things. For example, you might have some libraries that are associated with the some of the functions that you've called. So you'll need to also link those in with a linker. At the same time, it will then identify, okay, this is the code and this is where it's going to exist. The code may be something like, oh, here is some on-chip RAM up here. This is where we'll be able to store things like global variables. And oh, by the way, this is the space allocated for our special function registers or our peripheral I/O registers. These are things like, we'll look at this later, the timers, all the ports, including our UARTs, all those peripheral devices that we're going to be using later on. It also is going to identify, way at the bottom here, our code. And there are some special areas of the code. For example, really close to the bottom, in this area right here, usually you have identified for a table which says, whenever I have an exception, something bad going on, I know that I can go to this specific area and I can find an address and a register. I should say I could find an address, and that address will be code that I could run if I come across a problem. Oh, by the way, this is an example of one of my include files that I might pull in when I go through my C preprocessor. So I'm defining ports 0 through G, and it is telling me that, oh yeah, here it is at this location, at this location, at this location, etc., all the way down to 8C010. So where does that show up? Oh, here it is, 8. And then C000 would be where port 0 is. So maybe something like 80000 is some other peripheral device, an ADC or something else. We're going to see a little bit of that later. So, that is pretty much what I wanted to cover today in today's class. Again, this is if you look at the rest of chapter 4, it actually has some descriptions of how to use these IDE, some other files that exist in there. And I think you could probably read that as much as me explaining it to you. So make sure that you go through and read that so you have a flavor of what goes on. Thank you very much.